Right. Welcome back. We are back for another wonderful lecture. Linked lists today. Let's do it. Summer moves fast. There, I said my obligatory summer moves fast for the day. Let's get into it. So, test 3 is what we need to learn about how to do today. Test 3 is. Oh. Test 3 is the. There's a how do I want to word this? There's a pretty good difficulty spike from test 1 and 2 to test 3. Test 3 is where things start heating up. Test 4 gets a bit more difficult than that. And then the difficulty levels off mostly after that. So if you've gotten complacent with test 1 and 2 and said, you know what, I got this. First of all, you probably do got this. You got this. But test 3 is going to demand more of your time than test 1 and 2 did. Specifically, when you're asked to remove a rating, this is where you're expected to spend most of the time of the assignment is removing a rating by reviewer, and actually the testing requirements as well. Testing your code. Testing with linked lists is a bit trickier than the rest of the testing you've done before. This is where a lot of students see null pointer exceptions because they're not checking everything the way they're expected. One note on that, and things that I see a lot of students getting into trouble on test 2, a lot of the office hour and Piazza questions, is when you write these testing utility methods, the whole point of the testing utility method is to write this method and then call that method in your tests themselves. If you're not doing that, you're just asking for trouble. You're asking to miss some things. That's where when a reviewer creates a rating and you're testing that rating, and a lot of y'all will test the rating of that rating, the numeric value, but not check the reviewer ID of that value. You never make that mistake if you're using the compare ratings helper, the testing utility method that you wrote. If you create your expected object and then get your actual and then call your utility method, it's designed to get rid of a lot of those issues with you. This compare list of ratings is designed to prevent null pointer exceptions. So if you ever see a null pointer exception while you're doing test 3 testing, just remember what I'm saying right now. Use this compare lists of ratings. If you're using this and using it properly, actually, if you're just using it, you probably won't see any null pointer exceptions because you already solved that problem in the testing utility. But what not a lot of students, but the students that I see in office hours, what they do is write this method, get Autolab to check it off, and then basically throw it in the trash can and then redo all of that work when they get to the testing itself, which is just a lot of extra effort on your part. You're really going against the design of the assignment at that point. And if you need help using the utility method, I would love to take those questions in office hours. If you go, man, I just don't know. I wrote this compared list of ratings, but I just don't know how to use it. I would really enjoy that office hour visit. But the office hour visit of, I'm getting a null pointer exception. What's going on here? Well, and then I had to say, I said it right at the beginning of the lecture, so everybody was still paying attention at that point, whether you're watching live or the VOD. But I don't think those students watch lecture. I think it's part of the problem. Some of them do, and there's just 2.5 hours of content in each lecture, and you don't remember the thing I said right at the beginning. That's perfectly fine, too. I'm still going to answer all those questions in office hours, and I'll still be happy to do it. But there are ways we can prevent those. Questions. I have all the answers. Lectures where I give you every answer and prepare you for success. Okay, so to talk about linked lists first, I want to revisit array lists and arrays. This is how fundamentally arrays work. Array lists is a wrapper for arrays, and they behave a little different. Pretend that we can do more than this, but this is how our arrays work. First, there's sequential data structure, meaning that order does matter as opposed to hash map. Order doesn't matter in hash map or Python dictionaries. Those are non-sequential data structures. Arrays and array lists are sequential, meaning what the order that I insert things into an array list, I expect them to be in that order, and the array list will maintain that order. And something we haven't really talked about yet is it's one continuous block of memory. So when you ask for an array, you get one chunk of memory where all the indices, morning Jeshwant, but you get one chunk of memory and all the indices, like the value at index 0 is physically right next to the value at index 1 in memory. All the indices are right next to each other. And I say physically, it might not be actually physically because it's all abstracted through the operating system. But the memory address indices will be consecutive for an array, which means you, with just a little bit of math, you can find any value in an array. You take the size of any element in the array. So if you have an array list of ints, your element size is 32 bits or 4, why am I blanking on the math? 4 bytes. So your memory is always in bytes. So at one index is going to be a single byte value. So your array, the size of an array is 4 bytes, or size of, oh my goodness, size of an int is going to be 4 bytes for ints. So it depends on your data structure. If it's doubles, it's going to be 8 bytes. Multiply that element size by the index of the value you're looking for, and then add the memory address of the first value of your array. And this is what's going to be stored in your references. If you have a variable that stores an array, what it stores is the reference, which is the memory address for the first byte of the first value at index 0 of that array. So given that first address, which is stored in your variable, you can do one multiplication, one addition, and find the exact memory address of any value at any index very quickly. This is called random access. It's a very nice feature of arrays, and it's only enabled because we have one continuous block of memory. The downside of this is because we have one continuous block of memory, arrays cannot change size. Arrays are fixed size. They can never, ever, ever change size once they are created. Because we went to the operating system and said, I need enough memory for 5 ints in my array. And it said, here you go, here's your continuous block, big enough for 5 ints. And then we say, you know what, I would really like a 6th int. Give me the memory addresses right after those 5 memory, those 5 chunks of memory. Give me the next 4 bytes to store one more int. The operating system's going to tell us to go piss off. It doesn't work like that. The operating system does not allow us to ask for specific memory addresses, any specific locations in memory. It only allows us to ask for an amount of memory, and then it's up to the operating system to decide which actual exact memory locations to give you. So we say, give me this much memory, it gives it to us. We can't say, expand my array and give me the next bytes. Just not how it works. If it did work like that, well, things just wouldn't work, because what if another program is using the exact bytes that we requested? Now the software we write has to manage memory at a much lower level. It'd be a pain to write software, honestly. We just ask for an amount. So if you need to increase the size of an array, what you need to do is ask for, in that example we have, actually I forgot my numbers, say we want to grow our array to 8 ints, we have to go to the operating system and say, I would like enough space to store 8 ints. It's going to give us a location in memory for 8 ints. And then we're going to take our original array, copy all the values into the new array, and let the original array get garbage collected. And delete all our references to that one. And then just work with the brand new array. So that's how, and that's what an array list does, is it pretends that we can grow an array by once it runs out of space in the array, it'll ask for a new array. It'll actually ask for a new array of double the size of the previous array, and then move all the values over there. So that's array lists, and arrays more fundamentally. And on the, I explained a lot of this without the visual, oops. And the way it works in memory is you have one memory address stored in your variable. That's the memory address of the first value in your array. So say this is an array of 4 ints. Each int is 4 bytes. So the very first int is going to be at 0x200. This memory address, you can think of this as an index in a giant array. That's what memory is. It's a giant array of bytes that has billions of values, billions of indices. And at the index 200, we have the value, the int 10, the first byte of the value 10. So 10, this value at the first index, lives at 200, 201, 202, and 203 to get our 32 bits for that one int. And then if we want any value, we can use our formula here. If I want the value index 0, this part just zeroes out, and then we get just 0x200, the location at index 0. This is at least partly the reason why we start indices at 0. One is so this equation just kind of works out, but in general, it's so all the math just works out nice if we start indices at 0, or else we'd have to have index -1 here, or memory address, I don't know, -4, minus the size of it. We'd have to change this a little bit. And there's a lot of instances where that happens, where if we index at 0, the math just works out a lot cleaner. Everything's a lot more efficient than indexing at 1. So if we want the value at index 2, the size of an int is 4. We multiply it by 2. That's 8. Plus 200. That's going to give us 208. It's going to give us the indice of this value right here. And those of you who are really sharp on this, I forget every time to update this. I got to update it. But this should not be 212. This should be 20C, because it's hex values. Someday I'll fix that instead of just noting it in each lecture, but today's not that day. And the fact that we have that equation, that we can find any value in an array with just a little bit of math, this is called random access. I mentioned that in a previous slide. This is called random access, and it's why we call memory random access memory, or just RAM. That's why what we call it. But these days we kind of just call it memory. But we used to always call it RAM, and just over time it lengthened to memory. I don't know why that one happened. I'd prefer to just call it RAM still, just one syllable. But that's where this comes from. Random access memory. It's memory that can be randomly accessed because it's a giant array, and arrays work off of random access. Okay, compare that to a linked list. So I talk about that just to compare it to a linked list, because this is what we really want to talk about today. A linked list is spread all across memory. It is still a sequential data structure, so order does matter, but it's going to be all over in memory. It is not, very much not, one continuous block of memory. This is the key feature for a linked list, is it's all over memory. So each value in a linked list, which soon I'm going to start calling a node, each node, I'll do it right now, each node in a linked list knows exactly two things. Am I on screen? Two things. It knows the value or the element at that node, at that part of the list, and it knows where to find the next node. So each node in a linked list knows the value at that node, and it has a reference to the next node, and each node is going to be an object on the heap, which is exactly why this lecture, this content comes after classes and objects. It's because we need constructors, we need objects, we need references, we need all those things to understand how a linked list works. So to navigate a linked list, what you have is, instead of the memory address of the first index of an array, with a linked list, you have a memory address to the first object, the first node object of the list, and that list knows the first value in the list and a reference to the next node, which knows the second value of the list and a reference to the third node, which has its value at that part of the list, the third value in the list, and a reference to the next node, and so on and so forth, until we reach the end of the list, which I'm going to talk about on the next slide. The nice thing about this is linked lists are variable size. We don't have to do that. We ran out of space, give me a new linked list and copy everything over. We don't have to do that crap anymore. We do lose random access, but we gain variable size. These are the trade-offs between these two data structures. And data structures, by the way, are all about trade-offs. You'll learn about all of the trade-offs. I shouldn't say all, but a lot of different trade-offs between different data structures in CSE150. We get a taste of it here in 116. This is your taste comparing a linked list to an array. 250 is going to go into all of it, but throughout all of 250, it's going to be all about trade-offs. There is no one perfect data structure, or else we would just teach that one. There are trade-offs between all of them. So this is our trade-off with a linked list. It's variable size. If I want to add a new value to a linked list, I'll create a new node for the new value, and then I'll manipulate the references to add that node to the linked list. I don't have to destroy what I have or anything. I can just add it. In fact, I can add a new value to the middle of a linked list by updating a couple of references, and everything will just work just fine. So variable size, but we do lose random access, because if I need the last element in a linked list, I have to go to the first one, ask it where the second one is, ask it where the third one is, ask it where the fourth one is, and bounce all over memory until I get to the end of the list. So in a nutshell, that's linked lists. And I'll do this a lot throughout the rest of the semester. We're going to introduce a concept. Talking about like what the concept actually is doesn't take too long, and then it's 2 hours of reinforcing and examples and all kinds of stuff to really get you to understand what the concept is. So we have this linked list that's spread all across memory, all across the heap in different objects. Each object has two values. We're going to call that reference next. It's going to be stored in a variable called next when we get to the code. And the value at that part of the list we'll call value. And the reference, I already said that. But the new thing here is to know that we reached the end of the list. Because how do we know that we've reached the end of a list? For that, we're going to store for the next element, instead of storing a reference to an object, another linked list node object, we're going to store null. Null is a keyword that means what's supposed to be here, it's supposed to be a reference that is right here. That's supposed to be the value in this variable. This variable is supposed to store a reference, and it doesn't. That's what null means. So null means there's supposed to be a reference here, and there isn't. It's a null reference, meaning it does not refer to an actual object. And this is what we call null terminated. So when we're going through a list, how do we know we're at the end? Well, we're going to reach a node where its next is null. Once we see a node with a next of null, it does not have a reference to another node. Instead, it has this keyword null. That means it's the last node of the list. And all throughout our code with linked lists, we're going to have our null checks. We're going to say if next is null or if node is null. You're going to see that a lot today. Once we see null, we know we're at the end of the list. So our code, we have to check. Are we at the end of the list? If we're at the end of the list, we're going to do one thing. If we're not at the end of the list, we're going to do something else. So we're going to see lots and lots and lots of that. And this is your first taste of null termination in 220. Even your strings are going to be null terminated. Your arrays are going to be null terminated. So you will see this a lot in 220. CSE 220 is null termination. So get used to it this semester. Null indicating the end of some sequence. And here's the code for a linked list node. So I mentioned that we'll have objects on the heap. We'll have the linked list node class. Here it is, linked list node, and I'm going to slap int on the end here. So this linked list can only store ints, and we're not going to create any linked list class. We're only going to have linked list nodes and use those to represent our linked list. So a linked list node knows two things: the value at that part of the list and a reference to the next node in the list. We have a constructor to set those two values, and that's it. That's our linked list node class, and this is how we can use this to create linked lists and use this extensively. Now this is a little bit trimmed down from the final version of the linked list node that's in the repo, but this is the core of what we need. For one, our instance variables are private and we don't have getters and setters, so we can only use this code from within this class. So luckily my main method is inside this class, so I can access, oh actually I don't even access them. So I can access value in next, but we'll add getters and setters and write a few methods to work with these linked lists. But this is it. This is a linked list node. two instance variables. So every object of type linked list node, I create a new linked list node. I get copies of these two instance variables in that object on the heap. Oh, I should mention this explicitly. But if you're not, last Thursday we talked about objects and classes and constructors and all that stuff. At this point, you should be experts on that material. That would be the expectation at this point. Like if something in that lecture didn't make sense to you, you should have already gone through task 2. You should have already gone through task 2 by now. That should give you a lot of practice getting your hands on objects and constructors and all that stuff. And if there was anything else that still didn't make sense after doing the assignment, you should have studied that lecture, reviewed everything, because if you're still flaky on objects and constructors and stuff, you're just going to fall even more behind. This is why the expected deadlines are so tight, why the timeline is so tight, because if you go into linked lists not knowing classes, like, you're already lost at this slide right here, and we just started talking about linked lists. You cannot fall. This is true for any semester, but much more so in the summer. You can't fall behind at all, because if just imagine not knowing classes and being shaky on that and trying to understand what's going on here. It's not going to happen. You got to stay up to date on the material. Each lecture is building on the previous one for the most part. There's a few at the end that could be in parallel, but this one very much so builds on the previous one. The next one, Inheritance, is very much so going to build on classes. I guess not so much linked lists, but a lot of it builds. So we're going to create a new linked list node object. It's going to get values 1 for value and null for next. So this is a linked list of size 1. And then we're going to reassign first. This line often trips students up, so I want to talk about this a little bit. But we will do a memory diagram of this, like, soon. We're about to. But I want to explain the code first and then explain it again with a memory diagram. And hopefully with those 2 examples, we'll get this thing down. My dog likes to sit by my feet when I lecture. He's cute. So the variable first, the reason this is a little trippy is we have first on the right-hand side and first on the left-hand side. So it causes some confusion. If you break it down piece by piece, you'll see what's going on. But students who, I don't know, it trips students up sometimes. So we always resolve the right-hand side first. So first right now stores a reference to this node. So first is a reference to that node that was created on the first line of the main method. And then we're creating a new object with the value 2 and a reference to the original object. And then reassigning that reference that this resolves to, the new object, to the variable first, because that is now the first node in the linked list. And then we do it again. We create another linked list node with the value 3, and next being a reference to this node right here, and then reassign it the value first. So anyone, if you don't go through the code, I think this is what happens, is if you don't go through the code, if you just look at this and go, oh yeah, I know what that's going to do, without actually thinking about it and slowing down a bit, really digesting what you're looking at and analyzing everything, figuring out what's going on. If you're not doing all of that, you're going to think that this creates the linked list with the values 1, 2, 3. That would be somebody just glancing at this code, that's what they would end up saying. But if you actually break it down and look at what's happening, this is the linked list 3, 2, then 1. 1 is the last node in the list in this one. So we're effectively building the list backwards. We're prepending to the beginning of the list when we add nodes. This is in the context of like a quiz. If I give you something like this on a quiz, on the midterm, your trace should show that the linked list is 3, 2, 1. So some students will look at this and won't actually trace the code. Please, the reason I'm saying this is please don't do this for your own good. I don't want you to have to go to the final. Knock this stuff out on the midterm and be done with the quizzes. Is slow down, trace this one line at a time, one piece at a time. Make sure you get the right linked list. Don't look at this and go, oh yeah, I know what that's going to do, and then just kind of make up the whole memory diagram without actually tracing the code. Because those students should have to take the final exam, sorry to say. But if you're not actually tracing the code, yeah, you need to study more. until you actually start tracing code. Because if you're not tracing code, you're kind of defeating the purpose. You're going to be a weaker programmer. That's different than tracing the code incorrectly. Like if you just are still learning how to trace code, that's one thing. I'm talking about the laziness. Don't be lazy. But if you try your best and fall short, that's another thing. We can help with that. Come to office hours. We'll help you. We'll get you there. So and visually, this is what it looks like. I say each node stores a value and a reference to the next node. This is what it looks like. So first, our variable first from the previous code is going to store a reference to the first node in the list, which after all that code executes is the node with the value 3. And its next is a reference to the node that we created with the value 2. Its next is a reference to the node we created with the value 1. And its next is a reference to null, or rather the lack of a reference. So we know that this is the end of the list. Okay. Usually I would stop for questions in a live lecture, but since we have chat, you can just stop me at any time. Just chat whenever. Just whenever. Okay, we're at our first memory diagram, so let's grab some code. Week 5. Linked list node int. Got to remember my keyboard. I stream from PC, but my main laptop is what is even going on here? My main laptop is a Mac, so if you see me like looking at the keyboard, trying to figure out how a keyboard works, it's because I'm trying to switch like Alt and Control are backwards between the two. So that's what I'm doing when I'm staring at that, because I'm used to just I gotta break my muscle memory to hit the right keys here. Okay, so here's the code. We didn't talk about toString yet, so we're only going to trace these first 3 lines that we saw, but I want the rest of the code there because we are about to do toString. Our first algorithm for a linked list toString, we're going to do that one soon, so we'll keep the code here. Is that bus early? She made the bus. All right. So let's go through this code. Every Java program starts with the main method. And then the first line, we're going to have a constructor call. And this is going to be mostly just like the constructor calls we saw on last Thursday's lecture. So first is going to be assigned linked list node int. And this is going to return to this value. I'm going to put this just so I don't forget. And I'm going to create a new object on the heap, link it to that constructor, give it all of the instance variables, value and next, which are not initialized, so I'm not going to give them any values right now. Yes, they technically get values of 0 and null, but that's beyond what I need you to do for 116. We're not going to mess with those values, with the default values. It's just a memorization thing. We're not going to waste your time with memorization, waste your brain power on it. This is a reference to the object that's being created, and we have 2 constructor variables. This is where I think I kind of get students in trouble. Value gets 1 and next is null. Is a lot of the examples when we have constructors, the constructor will take all of the values for all of the instance variables. So I have value and next, so val and next, and then assign both of those using my constructor to initialize every instance variable. A lot of lecture examples will do that. And then I think students get tripped up and think, oh, that always has to be the case. The very first constructors I showed you did not do that. But then a lot of the examples just kind of happen. Like I want to initialize the instance variables through the constructor in a lot of my examples. But that is not always the case. If we only had one parameter here. We only put one on the stack. The instance variables do not automatically go on the stack. What goes on the stack are the parameters, whatever the parameters are. If there's no parameters here, the stack frame is just this with a reference to the object being created, no matter how many instance variables it has. So don't fall into that mistake. I see it way, way, way too often. So maybe I have to mix up my lecture examples. There's something I can do to help with that too. There always is something I can do to help with any misunderstandings. I got a lot of them in lecture now. A lot of misunderstandings don't exist anymore because I was able to improve things, but some of them are still there. So we initialize the variables. This returns a reference to the object we created, and we move on to the next line. First equals new linked list node, and we're going to do it again. So we have linked list node, this before I forget. It returns to the same variable first. Now when we linked list node, value damn it, Doc. Get out of my room now. So when I create this second object, I'm going to do the same thing. This is OX200. And when I resolve the values for the parameters, val and next, val is the value 2, and next, this is where we can clear up the confusion. First is on both sides of the assignment. Here, first, we have to resolve the right-hand side first, or you can think of it as we're resolving what's in the parentheses first. The arguments have to be resolved first. First, at this point in time, in the main method is OX100. It's going to be true until we resolve this thing. Like, it has to be first because we have to resolve this. We have to get the parameter a value before this method can return to the variable first. So this is going to be OX100 at this point in time. Then we run the constructor. Value gets 2. Next gets OX100. This returns, and then we update the variable. Once this returns, this resolves to OX200, and that's what's assigned to first. So first is reassigned OX200. And we get to the third constructor, and we do it again. So this, we get a new stack frame, another constructor call. Every constructor has a reference to the object that's being constructed. We have the type of the object being constructed, map the constructor, add all the instance variables to the constructor, value and next. This, we got OX300, add our two parameters, val and next. Val is 3, and next is whatever first is, and first is OX200, which shouldn't, I accidentally clicked, but it shouldn't be crossed out. Let's fix this. Oh, I could have fixed that easier. But it's OX200 right now. So OX200 right here. And then those get assigned because that's what the code is telling me to do. This dot value equals val. Each side of the equal sign is evaluated starting from the stack frame. So this dot next equals next. Next from the stack frame, we find it right here, OX200. This returns, and this is now OX300. And that's our linked list. That's where we're going to stop for now. We'll go back to the slides. But first, now stores a reference OX300, which is a reference to this node with the value 3. So if we're going through our list is just a reference to the first node of the list, which we often call the head node, or it's called the first node, or the head of the linked list. Sometimes it's referred to. And that reference takes us to this object here. So the first value in our linked list is 3. And then to find the rest of the list, we go to next. Next is a reference OX200. So this is our next node in the list. OX200, value is 2. Its next is OX100, value of 1. Next is null, which means we reach the end of the list. So this list has the values 3, 2, 1 in that order. So it's important, trace your code, go through it one step at a time, turn your brain off a little, don't overthink it, don't overanalyze the code while you're tracing specifically. Don't overanalyze it. Go through step by step and do what the code tells you to do, and you won't have to memorize anything here. Because really, I could give you is it at this point? Yeah, it's at this point. At this point, I could give you the data structures quiz, even though we hardly touched linked list and we haven't talked about trees at all, which are the 2 topics for the data structures quiz. Even though we haven't talked about most of those topics, you could do that quiz. You should be able to do that quiz right now. I won't say should, because if I gave it to you right now, I know the failure rate would be pretty high. We just haven't had enough practice with all the stuff yet. But you have everything you need to be able to do that data structures quiz, because we didn't do anything that's special to a linked list here. We did constructor calls, we did references, passing references through method calls, storing references on the heap. We did all this last time with the party and character example. We had references to objects stored on the heap. We even threw an array list in the mix there too. We had a reference on the stack to an object on the heap, which had a reference to an array list, which had references to characters. We were bouncing all over memory and everything. This example is a little simpler than that one, but we're talking about linked lists. I want to use this example still to motivate what a linked list looks like in memory. But if I gave this to you on a trace where you're not trying to figure out what a linked list looks like in memory at that point when you're taking that trace, you would be able to do that trace just knowing what you know about objects. And the same is true for trees. You don't really need to know trees. You just need to know how to trace constructors, how to follow references, and we'll also throw recursion on there. We're about to do recursion with toString. So if you're not comfortable with recursion yet, we only did one recursion example. So if you're not comfortable with recursion yet, that one's a bit tricky. In trees, the recursion gets a bit trickier too, to be fair. But there's no new concepts for data structures. For the OOP quiz, there's one more concept that I have to talk about with inheritance on Thursday, and then we'll be done with that as well. You would be able to do the midterm after Thursday's lecture, which, I mean, isn't that far off anyway. So we do inheritance on Thursday, then trees, and then the next lecture is the midterm. So we're not even that far away from it. We're only, after today's lecture, we're 2 lectures away from the midterm. But after, I think I made my point. Let's move on. Let's close these from last lecture. Get back to today. We did this memory diagram. And, I do want to point out one thing here, is the references are just made up. The memory diagram will do OX100, then 200, then 300. It'll go in that order every single time. But they could be random. If the tool made random values for those, that would be perfectly fine too. And when I do slides, I do just pick random, whatever values I'm feeling at that moment, I'll pick random values for those. So here I did OX480. Doesn't matter what this number is. It just means that go over to the heap and find your object 480. That has the value 3. Its next is 200. Oh, I said 480. 480. I like being proper on that. 200, value 2. Next is 350 right here. These values can be anywhere. It's what whenever the operating system decided to give us a chunk of memory at that point in time while our program was executing, which we have no way of actually knowing what it's going to be. If you run the same program twice, you're probably going to get different memory locations both times. There's no way to predict, and we also don't care. It has no effect on how our programs behave, so we really don't care about it. But just to emphasize the point that these can be anywhere. We ask the operating system for a chunk of memory that can store an int, for a linked list node object that can store an int and a reference to another linked list node. We don't care where that space is. We just care that the operating system gave us a reference to that memory address, to that location of the first byte of the memory that it allocated for us. Could be anywhere. All right, let's do toString. So we saw toString last time. Yeah, last time. We saw the toString method kind of briefly. It's a method, just to quickly recap. If we print something to the screen, its toString method will be called. Here I'm calling it explicitly because we're going to trace it. I want to make sure it's explicit. I had a few quizzes in the past where we just did print line of first would be the effective thing here. And it's easy to forget that that's going to actually call the toString method. And we had far too many students who did not trace the toString method, who were perfectly capable of tracing the toString method. They just didn't think of it at the time because usually print line, this is a method call that's internal to Java. And I say so many times in lecture, if it's internal to Java, we don't trace it. So they had a reasonable reason to not trace it. So I'll usually do it like this on quizzes now. If I'm having you trace a toString method, I'm going to do it this way. I'll call toString explicitly and then print it to the screen. But when you're writing code, you would just do system.println first and skip this explicit toString call. But that's the reason I split this into two lines. So here's my toString method. What it effectively does is prints out, converts all the values in the linked list to a string where all the values are separated by spaces. And we're using recursion. We're going to use lots of recursion. I am going to use recursion for all of my linked list examples, and I'm going to use it for all my tree examples as well. I don't want to give my whole recursion speech right now. I feel like I just gave a speech. So this uses recursion. So let's talk about it through a memory diagram. What else would we use? I guess there was no reason to go back to the slides there. I didn't really say anything. But so we have our toString method, and I didn't explain the code at all because I just want to explain it through a trace. The one thing I'll point out is this is a toString method that's calling itself. This is a recursive method, and we have a null check in here. But let me explain it through our memory diagram. So we're going to have our toString method call first. Let's get value on the screen here. Value is our variable, and we're going to call first.toString. So first.toString, we're calling toString from this object right here. So toString called from OX300. So this is the reference OX300. No parameters, so nothing else goes on the stack, and we're going right to the method call and running through this code. So we have out equals empty string, out equals empty string, and then out is immediately replaced with this dot value. So update this to this dot value, which is 3 as a string. And the only reason we're doing this is so we can use the concatenation operator to auto-convert this int into a string. If we could do this on one line, but in the 11 a.m. lecture when I live code this, I think I'll do it a different way. But this is just to do the string conversion is why this is broken up into two lines. So don't overthink this. Don't worry about this part too much. We're just getting the value as a string stored in the variable out. And then our null check. This one you do want to think about to understand for your coding when you're doing task 3. This is one of the big things that you have to do in all your methods that you write that work with a linked list. you're going to have to know when you've reached the end of the list. And we do that with a null check. If I say, don't forget your null checks, this is what I mean right here. We're going to say if we're not at the end of the list, is what I'm saying right here. So if this dot next, if the next value after this node is not null, that means this is not the end of the list. Or I could say, we'll often see in the next examples, this dot next equals null. If this dot next equal null, that means I know I am at the end of the list. So here I want to do something only if I have not reached the end of the list. So I'm going to check. If next isn't null, we're going to go head over to next. So if this dot next not equal to null, this dot next, that doesn't look like null to me. So we are going to execute what's inside this conditional, inside this block. I have no variables declared in this block, so I'm not going to worry about creating my code block on the stack. I'm just going to execute the code. Out plus equals empty string, space plus this dot next dot toString. So to complete this line, to execute this entire line in the assignment operator, I'm going to have to evaluate this method call first, this recursive method call. And there's two things I want to talk about here. Don't let me move on without talking about two things with this, what I have highlighted. So one, this dot next dot. We have two dot operators on the line. This is always going to store a reference to the object that called the method, OX300 in this case. Dot takes us to this object. Then we're reading its next variable. So this dot next resolves, in this case, to OX200. And importantly, it did not resolve to null. It didn't resolve to null because we just checked if it's null. We made sure it's not null. So we know, we absolutely know at this point right here that this dot next does not resolve to null because we just had our null check as the conditional for this if statement. And that's a very, very important thing, extremely important that we did that. Because if you have something that resolves to null, if this dot next did resolve to null, and we hit it with the dot operator, and the dot operator, just to recap, dot operator means what's to the left of me is a reference. I don't care about the reference. I want to go to the object. Take me to the object to which you refer. That's what the dot operator does. But if it's expecting, and the dot operator is always expecting a reference, whatever's to the left of it should resolve to a reference, and this dot next did resolve to a reference here. If it did not, if what's to the left of the dot operator resolves to null, and you ask null, hey null, take me to your object, null's going to say, bruh, I don't refer to any object. Like, that's what I am. That's what I do. That's my reason to exist, is to tell you that I don't refer to any object. I'm supposed to, like, what's supposed to be here is a reference, but I'm null. That means there ain't no reference here. That means I can't take you to any object, and that means your program crashes. You're going to get a null pointer exception. That means you tried to use the dot operator on a would-be reference that was actually null. So when you see null pointer exception, that's exactly what's happening. You have the dot operator on something that's null. And most of the time, at least by the time I see it, because if you have these errors in your code, it's easier to debug. You have your tests, you have the debugger and everything. Where it gets to office hours where it's not as intuitive and not as easy to see is when you write your tests and you submit to Autolab and your tests get a null pointer exception. That's what most of the Piazza and office hour questions are for test 3. It's always null pointer exceptions. This is by far the biggest thing, biggest question we get, and it's important to understand. So this is one of the common questions. The first one, I think, in this course, that's a common question that just kind of has to be a common question because it's a tough thing for everybody to really wrap their heads around. And we got to get you all there. We got to get you understanding this. So when your code is tested in Autolab, what's happening is your tests are written with your code, but your tests ran in Autolab, they're ran against intentionally incorrect solutions. So what a lot of students will do is make sure the list dot value, like first dot value equals something, whatever I'm expecting. Make sure assert less first dot next dot value equals whatever I'm expecting, and so on and so forth. And they'll manually check each value in the list, and maybe they're expecting the list to be size 4, and they check 4 values. And my incorrect solution returns a list of size 3. Now when they're checking that last value, one of their dot operators is working with null and following a null reference to the heap, and that's going to get you that null pointer exception every single time. So when you're testing linked lists, do not assume the size of the linked list is what you expect. Always assert that it is what you expect. So always assert, and you have assert not null available to you. You can use that one. And always assert that the value isn't null. Because if you're just assuming that what was returned is going to be a linked list of size 4 in that example, you're going to get null pointer exceptions when you submit to Autolab. You will. You'll get it. You'll get null pointer exceptions. And you won't get those in your code because your code is correctly returning a list of size 4. But when you're testing, you're often going to be testing incorrect solutions. If you're never testing an incorrect solution, that just means you're a god programmer and you never failed any one of your test cases. And in that case, maybe you can be the one person on the planet who doesn't need to write tests. And that, that's fine. You're special. If you're that coder, you won't see a null pointer exception anyway. Like, you won't be having this issue because you just understand everything. The rest of us who do need test cases to write effectively, to write quality code, just know that your test cases will fail sometimes, because sometimes you will be testing your broken code, and you don't want your test to error when that happens. You don't want your test to crash. You want your test to assert what was actually incorrect about that code. And if what was incorrect about it was it returned a list that was shorter than what's expected, you want a nice assert that's going to say, hey, the list was expected to be size 4, it was actually size 3, or something to that effect. The list wasn't what it was supposed to be. Do not just assume that the list is size 4. You will get null pointer exceptions, and if you can't figure it out, you will be in office hours talking about it. And that's fine. I'll be happy to help you still. I'll probably just repeat. I'll just hit a switch in my brain that tells me to repeat this speech that I'm giving right now, and you'll hear this. Honestly, in that situation, it might be the student hearing it for the first time, but maybe not. Like I said, 2.5 hours of lecture, you're not going to remember every single thing. So maybe I'll just have to give you a reminder, and that's fine too. It's fine if you don't get everything on the first round. But that's what a null pointer exception means. So hopefully spending some time on lecture, pausing everything and talking about it right now, hopefully it's... hopefully I prevented some of you from running into that issue. And the easiest way to avoid this, I did say at the top of lecture, I'll say it again here, maybe I'll find a way to say it again like halfway through as well, is use your utility method. Don't assert each node's value one at a time. Instead, create your expected linked list. Do the way, like we're creating a linked list right here. Create your linked list that is exactly the linked list that you expect to be returned, and manually create the linked list exactly like this, except obviously with the values and length that you expect. And then call compare linked list. Call the method you're testing, whatever it returns, call compare linked lists with those two lists, and then let your utility method do all of the work. If you do that, you can pretty much disregard everything that I just said about null pointers, because you're not going to see a null pointer in your testing. You just won't. Maybe when you're writing your utility method itself, but once you solve that problem once, don't set yourself up to have to solve the problem a second, third, and fourth time. Just call your utility method where you already solved the null pointer problem. Okay, so that was one. I said, don't let me go without two things. And I did forget what the second one was. I think it was about the recursive call. Yeah, it had to have been. I don't know what else it would be. So let's make this recursive call. So this dot next dot, we're going to follow the reference again. We got two dot operators in the same line. We get to this node right here, and we're going to call toString from this node. So we get another toString method call. This time, this is OX200. And then this stack frame, the first stack frame for toString, is going to sit there and wait for this method call to resolve so it can finish what it was doing. So this stack frame has to remember that this is where it was. It's waiting for this, and once this returns, it can finish writing this line. It can finish executing this line and then return whatever was resolved. So we have to resolve this execution, this method call first. In this stack frame, we have out is empty string. We're just going to execute the code one line at a time. Out is empty string. Out plus equals this dot value. This dot value is 2, and that's going to be converted to a string. Man, I did that again. It's going to be converted to a string. And then if this dot next not equal to null, this dot next, that doesn't look like null to me, so we're going to execute what's inside the code block, and that's going to be another recursive call. So this recursive call needs to be evaluated first before we can execute the rest of this line. So let's get toString on here. It's going to be this dot next dot toString called from this node right here. So this is OX100. And then we're going to start the method again. So we run the method again, out. But what's changing each time is the object that we're working with. And the way we're setting up the recursion here is we're going to have two different flavors today of recursion, of the way we're setting it up. This one is taking advantage of the keyword this. The method that we use to call the toString method, that's what's getting us closer to our base case of reaching the end of the list. So once we reach our base case, the recursion can end. We have a situation where the recursive call is not made, and we can start returning and resolving stack frames. And we're getting closer to that by advancing through the list, starting at the first node, then going to the second and the third. And we're doing that by leveraging the keyword this to advance to the next node. And by the end of the, actually not even the end of lecture, because we have stack and queue at the end. But not, I don't know, an hour from now probably, we're going to have an example where we're not going to leverage the keyword this, and we're going to see a different flavor of that. And I'll talk about it more when we get there. So we have toString, out is empty string, out plus equals this dot value. This dot value is 1. That's going to be as a string. And then if this dot next not equal to null, this dot next, well, that does look like null to me. So this condition is false. So we skip the recursive call, we skip the conditional, and just return out. So this is going to return out, which is the string 1. It's going to return it back to this stack frame. It's not returning directly into a variable, so I'm skipping my return arrows. If you wanted to do return arrows to the variable out, it's not technically correct, but I wouldn't be mad about it on a quiz either. So I'm not going to have any return arrow because we're not returning directly to a variable. So in this stack frame, we just had this resolved to the value 1 as a string, and we're going to do out plus equals space and then that value. So we have out equals out plus space plus this value. So what we end up with is 2 space, and then 1, the value that was returned from the other stack frame. There we go. So we updated the value of out, and then we're going to return out. So this returns 2 space 1 as a string to this stack frame, which was waiting for this to resolve. This resolved to 2 space 1. We have out, which is 3 plus space plus 2 space 1. So this is being updated to 3 space 2. Man, I just can't get that one right. Space 1. When do I hold shift? So we've updated out, and now we're returning out. This one does, of course I forgot my return arrow. This one does return to a variable. So this one gets crossed out. It's returning 3, 2, 1 all the way to the main stack frame. So value gets that 3 space 2 space 1, and then that's what's printed to the screen. 3, 2, 1. Then the whole program's over. Right. I'm going to take a really quick break. I'll be back in 1 minute. All right, what up? And that's the end of the first section of this lecture. Let me just double check. I'm quite certain. Sometimes I forget things though. Yeah, that's the end of this lecture. Done with those slides. So let's move on to linked list algorithms. So now that we know the structure of a linked list, I want to talk about algorithms to be able to work with them. And before we even do that, where'd my thing go? Before we even do that, we got to have my obligatory complaint about Windows. Why is it? How is it sorting things? It's not latest. Like this timestamp is after this one. So it's the latest date is on top, but it starts, no, these aren't even in order. It's sorted, this arrow says it's sorted by date modified, right? Now it is, but it was not. Does it not update when, oh, that's annoying. But first we got to talk about type parameters or generics in Java. I refuse to call them generics, but I will mention that they're called generics in Java. So this example was neat. We had a blast. I had a lot of fun, with this example. But I have one big issue with it. Is what if I want a linked list that stores something other than ints? Like this linked list is only ever going to store ints because we literally made a linked list node int, where it has an instance variable of type int. That's annoying. What I want is the flexibility that we have with array lists and hash maps, where we can give it any type. We can create an array list of integers, array list of strings, array list of players. We had an array list of characters last lecture. We can create an array list of anything. I want my linked lists to be that flexible. That's what I want, and that's what I shall have. So array list, we use this syntax to specify the type that's being stored in that specific array list. How do we set up that same syntax is our question for right now. I want to set up that syntax so I can say linked list node of integer equals new linked list node and then use this angle bracket syntax. So we got to flip this around and look at the other side, the class side. This is the object side where we're creating an object of this type. I want to flip that around to the class side and see what we have to do to our linked list node class to be able to enable this behavior and this functionality. So how are we going to do that? How do we do this? So let's do it. Okay, there it is. It's done. let's talk about this. So what we're going to do is when we declare, let me not get ahead of my slides for once, is every place where we used int, where we were saying int, we're going to replace that with a type variable. This is a variable that's going to store a type and resolve to a type when the type is specified at the object side. So for each object of type linked list node, this variable might store a different type. This is what I call a type parameter, and we have the type parameter list right in the class definition. We specify the name of the class and then the type parameter list. For all of our classes so far, the type parameter list has been empty and we just completely omit it. Now that we're going to use a type parameter, we're going to put it right here. This is our type parameter list. This says that the linked list node class takes one type parameter and we're going to call it t. T is a variable name. I can put anything I want. I can name it whatever I want. I chose capital T for reasons I'll talk about in another slide. Yeah, I'll say it at the end and hopefully not forget. No, never mind. I'll say it right now because I'll probably forget. Our type parameter variables, they are just variables. They're like any other variables, meaning you can name them however the hell you want. And Java won't yell at you about that. It'll let you name them whatever you want. But by convention, by naming conventions, if you want your code to be legible to other developers and you want to communicate effectively with other developers, which hopefully you do, eventually you're going to have to when you're working on a team. You want to communicate effectively, so you want your code to be more explicit, be more clean. Convention is a single capital letter for these. I chose T for type. Some people just choose A because it's the first letter. For array list, actually I don't remember what it is with array lists. With hash maps, there's two type parameters. So the type parameter list has two values, and it's just like any other parameter list. It's comma separated. And there it's K, capital V for key and value, because that makes sense. But it is a variable name, and by convention, one single capital letter. So if you're reading somebody's code and you see single types where you expect to type and there's a single capital letter, you know immediately that that's a type parameter. You know immediately what's going on there. Java calls type parameters generics. C++ calls them templates. I call them type parameters. I think that's the more language agnostic term to call them. I think that's the more generic term for them, besides generics. Is type parameter. So I have a type parameter T, and then when I want to use that type, I use it just like any other type. Just like you would any other type, I'm creating a variable, an instance variable of type T. I can take a parameter of type T. I can even use T as a type parameter for other variables, for other linked list nodes in this case. Hell, I could even create an array list of type T in this code if I had a situation where that was called for. But I'm going to use capital T wherever I need to use the type of whatever type this linked list node object is going to store. The class doesn't know what type each object of its type is going to be. If it did, we would just hard-code it again, as like we did with linked list node int. But if we don't know, we're going to just say, look, tell us what that type is going to be when you start using this class, when you start creating objects of its type, and specifically in the variables, when you create a variable of this type, That's when you tell us what t is for that specific variable or object. That's when you tell us. So I'm not creating just a linked list node. I'm creating a linked list node of integer. And now for this object, and again, Java doesn't make us repeat integer here. Since it sees it's being stored in a variable type integer, it's inferred that this is integer. If we were not storing this in a variable and we were just creating a new linked list node, then we would have to specify integer right here in this type parameter list, or type argument list at this point on this side. So we're specifying that t is integer for this object, and effectively all these t's will be integer. This constructor takes an integer and a linked list node of integer. The instance variables are integer and linked list node of integer. Everywhere where you see t, it's effectively integer for this specific linked list node object. It does not literally go to the code and change t to integer. In your assignment, you're going to create a linked list node of ratings, and do not. I see this. I actually haven't seen it in a while. This used to be a bigger issue, but I started giving this warning in lecture and stuff. This one I haven't seen in a while. Don't bring it back. I don't like seeing this one. Is what some students will do is go to the linked list node class, and they'll change t to rating to create a linked list node of rating. But that doesn't do anything because you just changed a variable name, which has no effect on your actual code. What the code does, you just you changed the variable name of t to the variable name of rating. That did not create a linked list node of ratings. When you create a linked list node of ratings, you want to do that at object time. When you're creating a new object on the heap, that's when you specify the type parameter. So you do linked list node of rating, new linked list node, and then you don't have to say rating again, but you can, if you put rating here or integer in this example, you can do that. That's fine. But this is where you specify rating to get a linked list node of rating or a linked list node of integer in this example. Don't change the type parameter variable name. That doesn't have any effect on your code. Just don't do it. Don't change the linked list node class at all. There's no need to. It's already in the repo. It's in the handout from task 1. It's already there for you. Just don't mess with it. Doesn't have any effect on your code if you change the name of the variable. And if we want a linked list node of a different type, so this we could do with the previous example with the linked list node int. But if we want this to be strings, we want a linked list node of strings. All the code is the same. The linked list node class doesn't change at all because this class now supports any type being stored in the linked list. We specify a different type argument when we create an object of this type, and then for this linked list node, t is effectively string in every instance. So now we have that full functionality that we had from array list, where we can have an array list of any type. We have the same thing in our linked list. We can specify the type for each node that we create. The only restriction here is that if we have a linked list node of some type, its next reference needs to still be of that type. And that's how we're enforcing our linked list, our entire list being one single type, which is it's what we want. We want that functionality. So we can't have a linked list of mixed types. We could actually do that. We don't want to in Java because that just causes all kind of problems. So we do want to enforce that next is going to be the same type, and we are enforcing that now. So we effectively have a linked list of strings. Okay. And that's type parameters. The advantage, well, I guess I said it a few times, but one more time. The advantage of this is we write the class once. We write the linked list node class one time, and then it can be used for any type. The Java developers wrote the ArrayList class one time, and when they wrote it, they don't even know what types it's going to be used for. They didn't know we were going to create an array list of characters last Thursday. They didn't know we were going to do that. The character class didn't even exist at the time that they wrote the ArrayList class. But since the ArrayList class uses a type parameter, it can still be used for that character class that didn't even exist when they wrote the ArrayList class. That's the type of flexibility we want with our code. We write code one time, and then we keep reusing it. And that's a theme that'll come up throughout your entire career. It's coming up right now. It's going to come up again on Thursday when we talk about when we talk about comparators and sorting, it's a feature that we really like. We don't want to have to keep revisiting our code and rewriting the same thing over and over because, well, now I want a linked list of parties and now I want a linked list of reviewers. Now I have to go write another linked list class for each of those types. We don't want to do that. You don't want to do that, right? You don't want every assignment to say, now create another linked list node class for movies. No, we're not doing that. So we write one linked list node class and then done with it. Have it take a type parameter and we're done. That's it. Okay, now on to the algorithms. So that was kind of a side note, but it's an important one. You got to understand type parameters because we're using them the rest of the semester. So let's talk about algorithms, and there are 5 specific algorithms that I want to talk about. First, let's add our getters and setters. No real surprises here. They're our standard getters and setters. You've known about these for a whole 5 days. It's not like they're that old news to you, but getters and setters I don't think are too complex. So we have our getter for the value instance variable. To return that, it's going to return a value of type t because that's what the type of that value is. So whatever t is for a specific linked list node object, that's the return type of get value. Set next and get next takes the next node or returns the next node, just like you would expect a getter and setter to do. It's a little different because it's a reference to an object, so there's a more complex type being involved, but it is either changing the value of an instance variable or returning the value of an instance variable, just like getters and setters were meant to do. One note that I do have that's not review is if there's something you don't want people to do with your instance variables, like here, I don't really want somebody changing the value of my linked list nodes, which is a somewhat arbitrary decision, but I just want to talk about this in lecture. If I don't want them changing the values of my linked list nodes, I just don't give them a setter. Easy day. It's a private variable with no setter. You can't change that. You're not allowed to. If you want to change the value of a linked list, you're going to have to manipulate references and change the structure of the list with a new node to be able to get that new that value change. Remove this node, create a new node, put it in its place. That's how you'd have to do it. So I just don't give them a setter if I don't want them changing the values, which can be useful. The one practical reason to do this with a linked list is if you have a bunch of code that's going to maintain a linked list in sorted order, and you don't want somebody going to some value in your list and to a node in your list and changing the value, they might break that sorted order and you no longer are guaranteed to be sorted. But if you don't let them change the values, then you can actually write some code that's going to enforce that it will always be sorted. This code, of course, they could change the references, the next reference, and still break the list. But that would be one reason why you might want to restrict what people can do is so they don't break the whole project by doing something silly. Okay, so let's get to the algorithms. So we know the structure of a linked list. Let's start working with this data structure. And let's just do some basic stuff with it to start understanding a little more in depth how a linked list works. And to that end, we want to write these 4 methods. Size, just tell me how many values are in this linked list. Append, add an element to the end of the list. So our first example, we were prepending, so we were adding elements to the beginning of the list, which is actually a lot easier with linked lists. We want to append to the end of the linked list. So we got to do a little more work to do that one. Find, give me the first node containing a specific value that we're looking for. And then finally, min. And min is the big one. This is the big finale that we want to absolutely get to. Min is going to have our... it's not how I want to word that sentence. Min is going to be the one most related to what you're asked to do on the assignment when we get to on task 3. So when we get to this one, I'll draw the parallels and I'll I'll explain all that. But we need to warm up to that. We can't just jump right into that because it'd be overwhelming. So let's do three simpler ones to get warmed up to the idea of writing algorithms that work with a linked list. And spoilers, it's going to be recursion and null checks. Those are the two big things that we have to think about. So let's do size. So here's my size method, and this is in the linked list node class. So again, I'm taking advantage of my recursive calls, getting a reference, getting the updated reference through the keyword this, because we're calling this method not through the same object that called the method that we're currently in, the stack frame we're currently in, but we're going to another node in the heap and then calling size from that node. So we're advancing through the list through recursive calls by taking advantage of the keyword this. And for size, we're going to check, are we at the end of the list? Is next equal to null? And this is where we got to think about how recursion works a little bit more and try to peel back the magic and defuse the magic, explain the magic, I guess. A recursive method, every time a recursive method is called, you pretend that what it was called on is the entire problem that you're trying to solve. In the case of a linked list, if this dot next is null, what I have is this is referring to a linked list that is size 1. Even if it's part of a linked list, it might be the end of a linked list of size 100 or 1,000 or 1,000,000,000. I don't care. With recursion, we're pretending that that is the entire list that we're working with. So whatever node called the size method, we pretend that that node is the head of the list, the first node in the list. Which is kind of true. If I have a linked list of size, well, actually I'll wait till we get a visual on screen for it. So we ask this node for its size. If it looks at next and it sees null, it's going to be like, I'm the only node. I'm the only one because next is null. Return 1. That is a list of size 1. If next is not null, what we're going to do is ask the next node for its size, and whatever it returns, we're going to add 1 to that and return it. So each node is either adding 1 or returning 1. That's all each node does, but this will give us the full size of any linked list. So let's see this in a visual. I'm going to do some like abbreviated traces, abbreviated memory diagrams for these. And we'll start seeing more of these in lecture, just mostly because, I mean, I got 4 examples of algorithms I want to do today. If I traced them all, we would never finish. We would never get through them all. So I'm going to do a little bit abbreviated. I'm not going to do the whole, this is on the heap and everything, but it will still be the same information, just really trimmed down in at a higher level, a different format. So somebody's going to call the size method on a node. So say this is our list with the values 4, 3, 1, and then null. So this is the end of the list. We're going to ask the head node of the list, the first node of the list, for its size. And this node doesn't know its size. So the only thing this node knows is its value and a reference to the next node in the list. That's it. It doesn't know much at all. It has no idea even if there's another node after this node. There could be 1,000 nodes after its next node. There could just be 1. There could be none after that node. It doesn't know. It just knows that next isn't null. That's the only thing this node knows. So it says, okay, next isn't null. So let me just ask the next node for its size. And if everything works, just zooming out and doing, we're not doing the full trace right now, so we can overanalyze a little bit here. And let's zoom out and try to think of what's going on here. Is this node is going to ask the next node for its size. If we ask this node for its size, what we would expect to be returned is 2. If this node is the head of the list, it's going to count itself plus this node and return the value 2. So as we go through the rest of the details of this, I'm hoping that this node eventually returns 2. This node's going to add itself to the equation and then return 3 to the original caller. That's what I want to happen. So let's make sure that is what happens. It is what happens. But so this node's going to ask the next node. This node's going to say, well, my next isn't null, so I have no idea what's going on after me. I'm just going to ask the next node, hey, how big are you? What's your size? And make that recursive call again. So now we have the original call on the stack, a recursive call, and another recursive call all on the stack right now. This recursive call, this node is going to check. This is now the calling object of the size method. So this is a reference to this node in that third stack frame. It's going to check its next, and it is null. So we reach the base case where we don't make any recursive calls, and it's just going to return 1. Thank you for the kind words. In Indracina, thank you. So it looks at next and it says, I'm the only node. I'm a list of size 1. So it's going to return 1. Hit the base case. It says, I'm the only node, return 1. So it finally reports the answer back to this node, which was waiting for this recursive call right here. This resolved to 1, which it doesn't matter what this returned to from this node's perspective. However many nodes is after it, this just returns some number, and then it knows, okay, if next is some size, whatever the recursive call returned, and I have a reference to that list, then I have to account for myself. I'm going to add 1 to that to account for myself, and then return 2 to whoever asked me about my size. And this node does the same thing. It gets the value 2 returned. It doesn't necessarily care what this resolved to. It happened to return to 2 here. It just knows that it is a list of that size of whatever comes after it plus 1. So it's going to add 1 to that 2, then return 3. You can imagine if this is a linked list of size 100, that first node is going to get the answer 99, add 1 to it, get to 100, and then return 100. And each node is just accounting for itself. So we're going all the way to the end of the list till we get to null, and then each node, the last node is going to return 1, and then each node just adds 1. 1 plus 1 to 2 plus 1 to 3. If it were a larger list, plus 1 to 4, plus 1 to 5, plus 1 to 6, etc. Each node just counts off 1 at a time until it gets the entire answer of every node in the list. Okay, and again, always as always, you can ask questions in chat. I'm not gonna, like in live lectures, I would pause right there for questions again. I'm just gonna blow through those pauses, and if you do have questions, hit me up in chat. As it usually takes students sometimes they have to sit there for 10 seconds before they summon the courage to raise their hand and stuff. But when it's chat, I don't think that's the same case. If it is, let me know, and I'll start pausing for questions. But so let's blow through this. Let's go to the next one, the append method. So before we prepended to the beginning of the list, we replaced the reference to the head of the list with a new linked list node with the new value, and its next was the old head of the list. So its next was the first node in the list, and then return its reference and replace the reference to the head of the list to that new node that was created. That was the first way we created a linked list. Now we want to append to the end. When we're writing code, it's kind of more common. Is that even true, or is it just what we do? Is to add to the end of a list, to add it to the last value. For that, we need append. And append, the first thing we have to do if we're going to append is get to the end of the list. So when we have a linked list in memory, it is only a reference to the first linked list node in the list. And that's it. That's all the information we have to start with. So to append to the end of the list, first we're going to have to traverse the entire list until we see null, and then add to the list. So we have to find the end of the list and then append to the end of the list. Where can we store the address of the new node so that the last node can append? Where can we store the address of the new node so the last node can append? In this example, we're not going to create the new node until we reach the end of the list. This is how we're going to get around that. If we wanted to append a node, like we wanted to write this method to append a node instead of a value, I would take that node as a parameter, then pass that parameter in all of my recursive calls. Like instead of value and being type T, I would have value be of type linked list node of T and say append this node to the end of the list, pass the node to every recursive call, and then just say this dot next equals that node if we want to do that. If I understood your question right, anyway. Where can we store the address of the new node so the last node can append it? Yeah, if we want to store it. But here, instead, I'm appending a value and then creating the new node only after we reach the end of the list. So if we're at the end of the list, then we found the place where we're going to append to. You don't have to apologize. Nothing to apologize for. But if I misinterpreted your question, just ask it again until we get there. We'll eventually get you a good answer. This dot next. If next is null, we're going to replace that null with a reference to a new node with the value we're appending and a next of null, because this new node that we're creating is now the end of the list, so its next has to be null, and it's going to have the value that we were appending. And then replace that old null with the new node with a next of null that effectively appended. If next is not null, we hit the else, and that's where we make our recursive call. We're going to say, well, I'm not the last node of the list, so I'm just going to tell the next node of the list that it's its responsibility to append to this value. And this recursive call will keep getting hit until we reach the end of the list where we're going to append. Oh, I got ahead of my slides again. So visually, say we have this list 4 and 3, and we want to add the node 1 or the value 1. We're going to tell the head of the list, hey, can you append, where can we store the address of the new node so that the last node's next can point to newly created node? Next. So I am doing that in this line right here. But I'm not storing, like I don't have to store it at all. I'm immediately assigning it to next. So there's no reason to store that address. We could do this in 2 lines. We could say linked list node of T new node equals this node, and then say this dot next equals new node. We could break it into 2 lines, but I'm avoiding the need for storage just by doing it all in 1 line here. Cool. All right, so we're going to add 1. We're going to tell the first node of the list, hey, add 1. First node of the list says, well, my next isn't null, so this isn't my responsibility. I'm just going to tell the next node that it needs to append this value. So it tells the next node, hey, we're appending 1. You take care of this. And this node is going to check its next. If next was another node, it would just tell the next node, hey, it's your responsibility. And each node is going to tell the next node, hey, it's your responsibility. Hey, it's your responsibility. Until we get to a node that has a next of null, which we got 2 right away in this example. This node says, oh, my next is null. I must be the end of the list. It is actually my responsibility, and I can't pass this on to anyone else because there's no one to pass it on to. That means it's my job to add this value to the list, and it's going to set its next. Instead of next being null, we know next is null because we hit the conditional. We're going to set next equal to a new node that we're creating. So we're going to create a brand new linked list node with the value that we're adding a next of null. And this object that we created, this new is going to return a reference to this object. And we assign that reference to the value of next that used to have a null pointer. Instead, it's now going to refer to the new object, and the new object refers to null with its next. So now we effectively appended 1 to the end of this list by making recursive calls until we found the end of the list, and then replacing the end of the list's next with a new node with a next of null and the value that we were appending. If we want to append another value, we want to append 10 to this list. We tell this node, it says, you append 10, you append 10. This node says, oh, my next is null, so it's my job. And then this node appends 10 right here. And this method returns void. So the original caller doesn't get any feedback. It just assumes that it worked. And it should work. I mean, with like when you call add on an array list, you don't need an array list to report back to you and say, I did my job. You just assume that it did its job. And hopefully the code's well tested and everything and does actually work, does do what it does. I can tell you append is doing what it's supposed to do. But you don't need any return value. So the caller just has to wonder if it worked, and hopefully they just assume that it worked for us. Okay, moving right on. Find, we want to find a specific value in a list. So given a value of type T, is it in the list? And more specifically, if it is in the list, return a reference to the node that contains that value, and specifically the first node. If the list contains this value multiple times, if there are duplicates in the list, return the first node would be the functionality we have here. Return a reference to the first node that contains this value. If the value is not in the list at all, return null. And otherwise, we're making a recursive call. So that's the functionality we want. Give me the first node that reference to the first node that stores this value, or null if it's not in the list. And this is pretty common with linked lists, is we want to return a reference to the node containing something. If we're looking for a specific node or a specific value or something, we usually want a reference to the node that has whatever we're looking for, because we need a reference to that node if we want to manipulate the list at all. If we want to add a value, so maybe we're finding a value so we can add a value to the list after that value, we want a reference to the node so we can say this node's next now has a new node that we're creating that we want to add to the middle of a list, which we actually won't do in 116, but that's why this is returning a reference to the node. It's so we can manipulate the linked list in creative ways. Maybe I should have y'all do that on homework, but deleting a node causes enough. It's enough. Go on with that one. There's no need to. Maybe someday. Not this summer. So if we're looking for a value, we call find. We're going to ask the first node, hey, do you have what we're looking for? Do you have this value 3? And it's going to check. It's going to go through these checks, and the order is very important here. It's going to check if it has the value that we're looking for. And we're going to use the dot equals method here. If the value that it stores is equal to the value we're looking for, it's going to return a reference to itself. This is a reference to the calling object, and that means we can return this. We can use this just like any other variable, including as a return value. That's false in this case. 3 is not equal to 4. So it's going to check the next thing. Our next condition is, are we at the end of the list? Because if we're at the end of the list, that means this value is not in this list at all, and we can safely just return null and say, hey, this value is not in the list. That was also false. We're not at the end of the list, so we're going to forward this to the next node, tell the next node to look for this value. So next node, find this value. And by the way, the theme of these recursive calls on a linked list is each call, like the code that you write, only has to handle a single node. You're figuring out what does one single node have to do, and once it does its stuff and it's not the end of the list, go to the next node through a recursive call, and that's going to effectively get you through the entire list. So we ask the next node, hey, do you have the value we're looking for? And it's going to say, yeah, my first conditional was true. If the linked list itself is empty, your variable will be assigned to null. When we get to the next example, actually, I'll have a lot more to say about that. But your variable that stores the linked list node, that variable itself will be equal to null. This is how we represent an empty linked list, at least in 116. That's how we do it. So this is true. 3 equals 3. So it's going to return a reference to itself, a reference to this node, and return that to the original caller, and it returns to the original caller. The original recursive stack frame, which returns to the original caller. It returns a reference to the node, to that node. So the original caller gets a reference to this node, which contains the value they were looking for. I said I didn't finish my sentence there, but I said the order is important here. You always want to process the node first and then check if you've reached the end of the list, if you have this specific setup, at least this specific task that you're accomplishing. If these two checks are reversed, if you're saying if this dot next equals null, return null, else if, check for the value, that's a big mistake, because if the value you're looking for is in the last node of the list, that last node never got its value checked, and you're going to return null. You're going to say, no, it's not in this list. So make sure you're careful with the order of these checks to make sure that the last node is being processed properly. And that's usually going to be one of the features I asked for. Like, you have to have a test case for that. What if the value is the last, like your edge cases for a linked list for your doing your testing, is the value of interest at the last node? Is it at the first node? And is it somewhere in the middle of the list? Those three test cases will pretty much get you there for testing, especially when it's deleting a node in test 3. What if the node you're deleting is the last node? What if it's the first node? And what if it's a node somewhere in the middle? If you get those three test cases, you write those three test cases and everything's working great, your code's probably going to be good. But you have to make sure if you have your test case for the last node, it's exposing this order issue. If you're checking for next equals null, then return null, then do your dot equals, you're not going to find that node. You're not going to find that value. Let's do another example where the value is not in the list. So we're looking for the value 8. We're going to ask the first node. It's going to say I have 4, not 8, and my next is not null. So I'm going to forward this problem to the next node. Hey, we're looking for 8. Hey node, do you have 8? Well, no, I don't have 8, and I'm not the end of the list, so I'm going to make a recursive call. We ask the next node, and it's going to say, well, I don't have 8, and I am the end of the list, so I'm going to return null. I'm the end of the list, next is null, and I don't have the value. The order matters here. You don't want to return null right away. In case this node did have the value 8, if your checks were reversed, it would return null before it ever checked for the value 8 to be able to return a reference to itself. So the order is important in these checks. But in this case, it doesn't have 8 anyway, so order was still important, but for this specific input, we're still returning null. So we return null. Each node, each recursive call is returning whatever the next recursive call returned. So this returned null. This resolves to null, and then the next stack frame returns null to the next stack frame for the first stack frame, which got the value null and returns null, return null, and the original caller is like, well, I didn't find what I was looking for. Well, crap. And I really snuck one by you here. So in all three of these methods, these three methods were structured mostly the same. There was more stuff to talk about with each one. They were designed to build on each other a bit. Really, the first 4 examples, counting the toString example from the that we traced, that we did the memory diagram with. So toString, size, append, and find all had similar flavors to them. And also, I got away with using this dot equals method, which really isn't going to get us very far. It's not going to help us very much using dot equals. Now, we used dot equals, and that worked fine because my example used ints, which capital I integer, because it's a type parameter, which does have a dot equals method, which is going to check if the two ints are equal to each other. But this isn't going to work for most types. Any type that we created did not have a dot equals method. It actually does, but it'll compare them by reference unless we override it, and that's stuff we haven't talked about yet. But it's also kind of a pain and doesn't even get everything we want it to. So our next example, I said we're going to find the min of 2 values. So dot equals is a special method that belongs to every single object ever. But min would require that we have some less than operator. And every object ever does not have a less than operator. We cannot do this. And it's important that dot equals does belong to every single object ever, because we're calling it through this dot value, which is of type T, and we don't know what type T is. Type T can be different for every single linked list we create. We know it's an object type because type parameters have to be objects. They cannot be primitives. So we know that we have an equals method because it is one of the special methods that exists in every single object ever. But you'll just have to take my word for that right now. We'll talk about that in an inheritance lecture on Thursday in a little more depth. ToString is also one of those special methods, so we got away with the ToString method. But that's it. Like, we're not getting away with much else. ToString and equals, there are a few other methods that belong to every object, but ToString and equals are the ones that are relevant to us in 116. And that's not much. There's not a lot we can do with those two methods. So we've really hit a wall of what we can do with these methods the way we're writing them here. So we need a different way to write our algorithms, our linked list algorithms, if we're ever going to do something like min or removing a node. Like what you actually have to do for the homework is removing a node by reviewer ID. So you have a linked list node of ratings, and you're given a reviewer ID, and you're removing the first rating with that reviewer ID. That doesn't exist in every single object. Like, you can't just do that. It's very ratings and reviewer specific. So we need a different strategy. All I have to say, we need a different strategy, and let's do it. So we want to find min, and min doesn't make sense unless we have a specific type. So we're specifically going to find the minimum of a linked list of doubles. So how are we going to set this up? And let me just give you the code so we can start explaining it. I gotta stretch a little. My back is feeling it. Ooh. So we're going to set this up instead of being inside the linked list node class like we had for the last 4 examples. We're going to do things a little bit different and create a separate class that's going to have a linked list, and it's abbreviated LL node, but this is linked list node. I just shortened it because specifically this line, I think it was the issue. This line just got too long, and then my code got too big, and then I didn't have enough room to put my text here. So I just shortened it for the slide. But LL node is just short for linked list node. It's the same exact class we've been using all lecture. So I'm going to have a class that's going to have an instance variable of type linked list node of the type that I want. And this parallels your task 3 pretty directly. And let me not be coy about it. Let me be very explicit. Linked list of doubles is going to be your song class, and it's going to have a linked list node of ratings as an instance variable. And when you first initialize a linked list, when you have a variable of type linked list node here, getting back to the question in chat, when you have a linked list node variable, I have numbers here as my variable, it's initially empty, and to specify an empty linked list in 116, different applications, different languages, different places are going to have different ways to represent this. In the context of CSE116, an empty linked list, we assign the variable to null directly. Anything else is wrong. Don't do anything else. This is one of those things where I will see the wrong thing so many times. I still can't figure out where the confusion is. I want to update my lectures to get rid of the confusion. I just don't have, I haven't figured it out yet, how to avoid it. What way too many students will do is they'll say, I have an empty linked list, so I'm going to set it equal to a new linked list node of null. So many students do that. I'm so sick of seeing it. It's so often it happens. Don't do that. Don't do it. Don't do it. This is how we right here. The variable of type linked list node equals null directly. This is a linked list of size 0. If you have a new linked list node of null, that's a linked list of size 1, and the one value it stores is the value null, which is, I will never do in lecture. I'll never show you that. I'll never expect you to do that. It's not something we do in 116, ever. Yet I will see it in office hours multiple times. And I just don't know where it comes from. I have my speculation of where it comes from, and it's not a good thing. But I don't know. I've never seen a reasonable explanation for why a student has done that that didn't involve. Well, let's not talk about it. Uh, so this is our the way we're going to use our linked list in the homework is we have our song class, which stores a linked list node of ratings with some name, and then initially it'll be equal to null. And then we need some way to actually add things to it. So I have an add double method. This is going to be an add rating method in your homework. This method here completely parallels what add rating should be. You shouldn't have any questions about how to write the add rating method because it's going to be exactly this. You just replace double with rating. It will be exactly this method. That method is 100% given to you right here. There's no expectation that you're going to spend any significant time writing the add ratings method. So let's talk about what this method does. Is we have some new value that we want to add to the linked list, the underlying linked list in the instance variable. And we're going to, we want to append the values. The order is going to matter to us. We want to append this value. So we could just write this dot numbers dot append. We have an append method in the linked list node itself. It's given to you. I don't think it's in the repo in the handout code. I haven't mentioned this yet in the summer. Is any code that I show you in lecture and any code in the examples repo that's linked from the top of the course website. Any code that's in that repo, which includes the code that I show in lectures, all of that is fair game to just cut and paste into your homework solutions. So what we just did, the append method, we covered it in lecture. There's no expectation that you're going to recreate that from memory or anything. You can just cut and paste that method from the repo because we went over it in lecture. Like I told you explicitly what the method is, every line of code, we went through it all. You can just use that. So you can grab that and put it in your linked list node class in the homework and then use this exact method here. So we could just call the append method. The problem with just straight up calling append and having this be a one-line method is that when numbers is initially created, it is null. If we do this dot numbers dot, we're going to get a null pointer exception every single time. Because it's initially null, once we add our first thing into this list, our first value into the list, this dot numbers dot null pointer exception, program crashes. We never get to the append call at all. So we have to fix this, and we fix it with a null check. Linked lists in your homework, you should have lots of null checks. You're going to have as many as you need. Pretty much every method you write is going to have a null check. This dot numbers, if it is null, so if we have the empty list, if we have nothing in this list yet, then we're going to add that first value. This dot numbers is a new node with the first value of the list and a next of null. We have a list of size 1 right now because we just added the first value. And as long as numbers isn't null, we're going to leverage the append method that we already went over in lecture and let the append method traverse the list until it finds null and then append to the end. Now in your add rating method, if you want to recreate the append method for any reason, I would actually recommend it for extra practice. I say you can use the append method from lecture just because I have no convenient way to like flash your memory and make you forget about the lecture content so you can rewrite the append method. I have no way of doing that, so I just explicitly allow it since if I don't, most of you are going to do it anyway because, you know, we covered it in lecture. You have a valid excuse. Your code looks like lecture code. Well, yeah, because you covered it in lecture. Yeah, okay, that makes sense. I might as well just explicitly allow it. So your add rating method looks pretty much identical to this. And then the min method. This is the one we want to talk about. The rest of, not the rest of the lecture, but the rest of this section of lecture is the min method. I want to use recursion just because I want to use recursion. Should we have the recursion talk right now? I guess we should. There's so many of these little things I got to get in there, but let's do it. I'm using recursion for all my linked list examples. A lot of you choose historically speaking, a lot of students choose not to use recursion on task 3 when dealing with linked lists. I recommend that you do use recursion. This is a warning that goes mostly unheeded. You know, a lot of you, historically speaking, will just use loops for your stuff, for your linked list stuff. I'm not even going to show you how to use a linked list with these. So if I see loops in your code, I know you went off on your own and did that. Because I'm not even going to show you how to do this with a loop. Because I recommend you get practice with recursion, because when we get to the trees assignment, task 5, you won't be able to use loops, at least not easily. You won't want to use loops anymore. You will be using recursion on task 5. So if you're, and the recursion is a lot more, I shouldn't say a lot more, but it's more complex writing recursive methods for trees than it is for linked lists. So if the task 5 tree recursion is the first recursion you ever do, you're kind of setting yourself up for failure. Not necessarily failure, like especially not in the course, but failure in the sense that task 5 is going to take you way longer than it should, because you're going to catch up on all the recursion practice that you skipped on task 3. So I really recommend using recursion for task 3. So by the time you get to task 5, you're already used to using recursion, and the only thing you have to add to that is, how do I do tree recursion, where there will be 2 recursive calls in each method, because you have to follow both branches of the tree. Writing tree algorithms without recursion is not going to help you. I'll say anyone who is capable, I think this is a fair statement, anybody who's capable of writing the tree algorithms without recursion will have absolutely zero trouble writing them with recursion. You will not use loops on trees. You will not avoid recursion on trees to make your life easier. That is a guarantee. It is way, way, way harder to avoid recursion on trees than it is to just embrace recursion. So that's my advice. That's my recommendation. I'll try to leave it at that. But you get your recursion practice now on linked lists while the recursion is still easy. That's my recommendation. All right, so I want to use recursion for the min method, but I have a problem here. When somebody calls the min method, I want the public-facing method that they call to take no parameters. If somebody wants the min of a linked list, this linked list of doubles, they're going to create their linked list of doubles, they're going to add some doubles to it, and they just want to call the min method. Hey, min, give me the minimum value. That's it. They shouldn't have to tell me anything else. They're telling me everything they need to tell me through the fact that they're calling the min method. They want to find the minimum value in this linked list. The problem is, my recursion, the only meaningful way I have to send information to the next stack frame is through parameters. So I want parameters. In fact, for this one, I'm going to want 2 parameters, a reference to the node that I'm currently working with, that I'm currently visiting, and the minimum value that I've seen so far through all the nodes that I've already processed. I want these 2 pieces of information. But I don't have them here. So what I'm going to do is write a helper method. When I want to set up recursion, if I don't have the parameters I want, I'm going to write a helper method with whatever parameters I want, whatever information I want to pass from one recursive call to the next. I'm going to create a helper method with those parameters. And for this, I want the node and the minimum value that I've found so far. Pretty much like for the accumulator pattern, when we were doing the min, like, what does that loop need to know? That's what your recursion is going to need to know. Those are going to be your parameters. So I have these parameters, and then my min method itself, my public-facing one, is just going to call the helper method with the initial values for my... Got to update this slide too. With the initial values for my recursion. So it's going to start at the head of the list, this.numbers, the head of the list. So we're starting at the first node, and then some value that's not going to mess with my calculations. This was originally an integer example, and I changed it to doubles, and then I missed this. I didn't update this integer. This should say double dot positive infinity instead of integer dot max value. But something that's so ridiculously large that whatever the value of the first node is, it's going to override this and replace it with its own value. And we have to have one special case. We always have to have our null checks. If the list is empty, we need to return some value, and on the this value is meaningless here, but on the handout I have to say something like, if the list is empty, return -1, and just kind of make up some value. What should be the return value? This is a pretty bad return value, admittedly, because it looks like the minimum value of the list was -1 instead of indicating that there was an issue and that there was no value. Probably double dot positive infinity would probably be the best one to return here. And then when we finally get to the helper, oh, I'm getting way ahead of my slides. I'm just explaining the whole thing. And then when we finally get to the helper method, we're going to keep track of the node we're currently visiting through this reference node. This is different than what we did in the previous 4 examples. So we're going to pass the head of the list, the first node of the list, as our starting node. And then as we make our recursive calls, we're going to advance to the next node, and we're going to use our getters and set it, well, just our getters here. We're going to use our getters because we're no longer in the linked list node class itself, so we have no access to the private variables. In the previous examples, I was just doing .next and .value. Can't do that anymore. I got to use my getters at this point, which you're going to have to do on your assignment too. You're going to have to use the getters and setters because you're not going to modify the linked list node class, aside from potentially adding append if you want to use that. You'll be using the getters and setters. So we want to start at the first node. And with the previous 4 examples, we didn't have to do this because we were leveraging the keyword this to advance to the next node. And the only reason we were able to do that was, again, because we were in the linked list node class itself. So this was a reference to a linked list node. And if we did this.next.recursive call, this in that recursive call would be a reference to the next linked list node. But now that we're in the linked list of doubles class, we're outside of the linked list node class, or for your homework when you're going to be in the song class for this, with a linked list of ratings as your instance variable. When you're in the song class, this is going to be a reference to a song, and you can't do the same thing. You can't like advance to the next song. There's only one song, and that song has a bunch of ratings. You need to advance to the next rating, the next linked list node, but from a class that's not linked list node. So we can't use that trick we've been using. We can't leverage the keyword this, because this is always going to be a reference to the same linked list of doubles object, the same song object. It's just not useful to us anymore. So we're not using the keyword this, because we can't. It's not doing it for us. So instead of using the keyword this, we're going to move that linked list node, the reference to the linked list node that we're currently visiting, to a parameter, start at the head of the list, and then make our recursive calls on get next to be able to advance to the next node. Instead of calling the recursive call through next, we're going to make the recursive call and give it an argument of next, so the parameter is going to be the next node in that next recursive call. So a node is always a reference to the node that we're currently visiting, the same way we were previously using the keyword this. And nobody has to care that we have this private helper method. Anybody calling the min method doesn't even have to care that we used recursion or anything. So make it private, encapsulate the details, and then have a public-facing interface for other people to call your code. They'll call it through the min method that takes no parameters. They don't care that we have this helper method that takes 2 parameters and sets up recursion. Hide the details. Okay, and then our actual method, we have our null check as always. If the node we're currently looking at is null, so we will have a situation where the parameter here, node, has the value null. The way I'll explain when we get to the second part too, is if it's null, we'll just return min, which is the minimum value seen so far. If we reach the end of the list, we've seen all the values, and that is the overall min of the list, the entire list. If we're not at the end of the list yet, we're going to get the node's value, the node we're currently processing. We're going to get its value and check if it is less than min. If it's less than min, we have ourselves a new min. So we're going to return whatever the recursive call returns. We're going to make a recursive call, advance to the next node in the list so we can process the next node, and pass it the value at this node. Since this node's value is less than min, this node's value is now the new min in the next stack frame. If this node's value is not less than min, we're going to keep the old min. We're going to make the recursive call, same recursive call, but with the old min, because we didn't find a new minimum value. And then return whatever those recursive calls return. So we're going to put recursive calls on the stack until we get to the end of the list. Once we get to the end of the list, min will have been replaced possibly multiple times and will be the minimum value in the overall list. And then we can return that, and then each recursive call returns what the next recursive call return. So return min, and then all the rest just return, 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 return. And then return it all the way up to whoever initially called min, and they get the minimum value in the list. Okay, I'm going to skip these slides for a reason that will be apparent in 1 second. And go to stack and queue slides. Now that one did order the right way. It's weird. But first, deleting a node. So I skipped the slides on the last one. It's because I have them right here. They're the same slides. I just wanted to switch to the next slide deck. Oh, excuse me. All right, so let's talk about deleting a node. This is what you have to do in your assignment. This is the bulk of it. I said, oh, let me revisit the assignment description. So what you're asked to do is create in the song class, you're going to create that instance variable for a linked list of ratings. You can create the add rating method, which we went over. It's the add double method. It's the same exact thing, just rating instead of double. And you're going to have to you're going to have to grab the append class, the append method from the examples repo, or rewrite your own append method. It's fine too. Get ratings is just a getter. It's just going to return the instance variable. Set ratings, it's just a setter. It's going to set the ratings instance variable. And then average rating and remove rating by reviewer. These are the two methods where I expect you to actually be putting in some work. Average rating is is your first kind of warm-up algorithm where you're going through all the ratings in the list, ignoring any invalid ratings, and then taking the average of whatever ratings are actually valid ratings, every valid rating. So kind of a warm-up going through a linked list and doing a little bit of calculation. And then the big show here, remove rating by reviewer. I would expect you to spend, 75% of your time on this assignment just on this method and the testing. You're going to test average rating and remove rating by reviewer. So the testing is going to take a while, especially if you didn't take my advice from earlier and you're doing your checks manually. You're going to get null pointer exceptions and you're going to be confused by it. If you're taking my advice and using the utility method, then remove rating, average rating, you won't see null pointer exceptions. But remove rating by reviewer, if you're using compare lists of ratings to set up your test cases, then you're not going to see null pointer exceptions. And this should be pretty straightforward. It'll take time just to come up with your test cases and just type them all out. But remove ratings and testing remove ratings, this will be the bulk of the time that you spend on this. Actually, compare lists of ratings takes a little bit of time too, especially if you don't catch, if you're still thinking about how a linked list works when you're writing this can take a little bit of time. Especially if it's the first thing that you write, which if you follow the structure of the assignment is the recommended first thing you write. So it can take a while if it's the first linked list code that you write. But remove ratings by reviewer, this is the big one. So for this, you have to remove a specific node by a given reviewer ID. And how do we do that? And for this one, I'm not going to show you the code at all. This is for you to figure out. The because since this is what the homework is really asking you to do. This is the crux of, do you understand linked lists? If you can delete a node by reviewer ID when the nodes have values of ratings, if you can do that, you're doing good with linked lists. So I do want to explain the concept of deleting a node, but we're not going to show any code for deleting a node. So let's say I want to delete this node. I ran some code, I have some code and logic that decided I want to remove this node with the value 2. I want to remove this node right here. So if I want to remove this node, I actually need a reference to the previous node in the list. I need this node here, a reference to this node, if I want to delete the node that comes after it. And the way I'm going to delete that node is actually really conceptually really simple. I'm going to take the node before the node I want to delete, and I'm going to set its next equal to its next's next. So I'm going to say this node's next equals its next dot next. So whatever its next node is referring to as its next, we're going to update this node's next to that next node. So a lot of next going on there. But what we're effectively doing is cutting this node out of the list. We're just advancing this next to the next node and bypassing this node entirely. So this node is effectively deleted from the list. Technically, we still have the list 2, 1 in memory, but our overall list, if we have a reference to this node right here that we think of as storing our list, that list is now 4, 3, 1, and that's the end of the list. We effectively cut 2 out of that list because it'll never be found. There's nothing referring to this node anymore. In fact, that node's actually going to be garbage collected. We don't have a reference to it anymore. We have no way of ever accessing it ever again. So Java's going to say, let me clean that up for you. There are edge cases. I mentioned these already, but now that we have the visual, there are a few edge cases here. Deleting the last node, which isn't quite an edge case because the logic is still the same. Next is null. So this node will now just naturally get a next of null. It'll cut this out of the list, and this will be the last node in the list. What is more of an edge case is removing the first node in the list. To remove the first node in a list, the way we have the song class set up, you're going to update the instance variable itself. The instance variable refers to the first node in the list. You would want that instance variable, instead of referring to this node, update the instance variable to refer to its next node. So you would have the instance variable refer to this node instead. So that one does take a little bit more work in your code. You should absolutely have a test case for removing the first node in the list and a test case for removing the last node. The reason the last node's an edge case is because of what we talked about with finding a node, the order of your checks. If you're checking for 1 and you check for null first and say, I'm the end of the list, we're done here, without checking the last node's value, that's a very common mistake, so we want a test case to catch that. And when you're going through the list, you have to have 2 nodes in memory at the same time, where you have to look ahead. There's some extra stuff to do because you need a reference to the node that comes before the node you want to delete. You can't traverse the list and just look at that one node because you'll need a reference. You say, oh, this is the node I want to delete. You need a reference to the node that comes before it. So you kind of got to look ahead and store a reference to the node that comes before the node you're actually considering for deletion when you're going through that method. So those are all my hints for that method. Let's get on to stacks and queues. So stacks and queues in not a lot of time. The stacks and queues lecture is always pretty late, so I think we got this still. So stacks and queues, they're stripped down data structures. What I mean by that is, at least in the context of today, we're going to build a stack and a queue out of a linked list. We're going to use linked lists to build both these data structures, and they're going to have, with one exception, with a queue. The queue is going to have a little bit of extra functionality, but with that one exception, these data structures will have less functionality than just a linked list. So in most cases, you would just use a linked list instead of these data structures themselves, the data structures we're about to build, but you would use the concept of a stack and queue. These are 2 topics that are very important by concept. The concept of stacks and queues are very important. And the reason for that is all their operations. They have stripped down functionality, but all the functionality they have left will be extremely efficient. We won't have a ton of time to go deep into it, but 250 will absolutely go way deep into runtime analysis. And what we're going to see with stacks and queues is that every method on these data structures is an O of 1 or constant time algorithm, meaning they're very fast. That's about as much depth as I'll have time to go into right now. They're very fast, very, very fast data structures. Even when there are billions of elements in these things, they're extremely fast. So a stack is our typical last in, first out data structure, meaning whatever you put in last is the first one that comes off. The last stack frame that you add to the stack, that's the only one that you can remove from the stack. It's the last one you added. It has to be the first one you remove because it's covering up all the other stack frames. You have your main stack frame way at the bottom. The only way to reach that is to have all your other stack frames return and get back to that bottom stack frame. With the stack and that's all I want to say actually. But it absolutely is, the memory stack is an actual stack data structure in concept. Now we draw the stack upside down in our memory diagrams so the top of the stack is visually on the bottom. But that is exactly what's happening. That active stack frame is the top of the stack. It's the only stack frame that's active, and to get to any stack frames below it, we would have to pop that off of the stack, or in the case of stack frames, that stack frame has to return. Once it returns, it is removed from memory, and whatever stack frame's underneath it, that's the one that's active again. So stacks are defined by two methods, push and pop. And that's it. Push and pop, period. That's it. That's all you get. Push is going to add an element to the top of the stack. Pop removes an element from the top of the stack, and that's it. That's all you get. Certain implementations of a stack will often give you a third method called peek or top, or I forget what else it's called. Peek and top, I think, are the two common ones that will let you look at the top element on the stack without removing it. And some implementations will even give you like a size. Different implementations will give you different methods. But these are the two that define the concept of a stack. If you got these two methods, that's your stack. And anything else is just quality of life improvement, just giving us extra functionality for a stack. But those are the only two you really need, is push and pop. And how this works in the code, if I create a new stack, and we're going to use type parameters for our stacks, if we create a new stack and we push values to it, we're pushing 1, we're going to push 2 to the top of the stack, push 3 to the top of the stack, and when we pop is doing double duty. It's removing the top element from the stack and also returning the value of that element. So X gets the value 3, and 3 was popped off of the stack. That's why some implementations give you a top or peek method in case you want to know what's on the top of the stack without actually removing it. You can still do it with push and pop. You would pop the value, take a look at it, do whatever your code needs to do with it, and then push it back onto the stack. So you can get that same peek functionality, but it's not as intuitive. And here's my implementation of a stack. So we're going to use a linked list node. This is similar to the linked list of doubles, where we have a class that's going to have a linked list node as an instance variable, same as the way your song class is going to be set up, in that sense that it's going to be the song class with an instance variable type linked list node. We want the same thing with a stack. Stack is going to take a type parameter and forward that type parameter right to that linked list node. Initially, top is empty, so we assign it the value null. I could do this inline up here like we did in the last one, or initialize it in the constructor like this. And in fact, the default value for an object is null, so I actually don't have to do anything, but I want to make sure it's explicit so you can all see what's going on with that. Push is going to take a value, and it's going to be our prepend operation. We want to push to the front of the stack. It's going to make our stack a lot easier to implement. If we have to go to the end of the stack, we have to traverse to the end and do append, and then to pop, we have to traverse to the end and then remove that node. With prepend, if we're working at the beginning of the list, It's a lot easier to work with. We already have a reference to the beginning of the list, so we'll build our stack from the beginning. And that's going to give us very efficient operations. We just have to manipulate that front node. So prepend, we didn't see this in a method before, but this is a prepend method. We saw it in our very first linked list example when we manually created that 321 list. We're going to create our new linked list node, which has a reference to the old top of the stack, and then update our instance variable to that new node. We could also do this in one line like we did before, this dot top equals new linked list node value this dot top. That would also do the same thing that we're doing here. And notice that we don't need any null checks here. If top is null, if the list is empty, we're going to get a new node with the value we're pushing, and next is null. And that's fine. It's perfectly fine. That's exactly what we want, so no worries there. When we pop, we're going to check if the top is null. That means we have an empty stack and we're popping off an empty stack. A lot of implementations of a stack will actually crash your program. It'll throw an exception if you pop off an empty stack. For our implementation, we're going to return null just because we're not going to pop off an empty stack anyway, but we have to have something here. We're going to return null. If the stack is not empty, we just need something so we don't get a null pointer exception if we happen to do that. And then if the stack is not empty, we're going to get the value of the top of the stack because we have to return it. We have to also remove the top of the stack, but we need to grab the value of the top of the stack before we remove that node, because once we pop that node, there's no way to access it anymore. It's going to get garbage collected, and we can no longer access its value. So we're going to grab its value, put it in some temporary variable so we can return it, and then update the top of the stack. This dot top is updated to the top's next. We're effectively deleting the first node in the linked list, or popping that node off of the stack. Did I just blow way ahead of my slides again? I gotta stop doing that. Push and pop. I already explained it all. And then another abbreviated memory diagram. So when we push to the stack, so say we executed all this code, we created a new stack, top was null, then we pushed 3, top was a reference to this node, then top was a reference to 7, then to 2 at this point, and then say we want to push -5. If we push -5, we're going to create a new node that refers to the old head of the list, and then update the head of the list variable, which is top here, to the new node we just created. And notice, I'm not going to dwell on it here, so we're short on time, but notice nothing inside this box changed. This whole linked list is completely preserved and completely reused in memory. 100% unchanged. So to prepend this node, we had to do very little work. We created a node and then had to refer to the old list. And it doesn't matter how big that list is because we don't have to change that list at all. We just create the new node and update one reference. That's a constant amount of work, meaning it doesn't depend on the size of the list. When we want to pop, we're going to update top to a reference to the second node in the list and return -5, so x will get -5. And then this node will be garbage collected. We no longer have a reference to it. It's going to be deleted. Well, it is deleted, but it's going to be garbage collected. Oh, and thank you, slide. And all these operations are O of 1. Nothing there depended on the size of the list. We just worked with that reference, and nowhere in here are we traversing a list. Hell, we don't even have any recursive calls here. We don't have to traverse a list at all. We're never going down the list more than one single node to push or pop. Other algorithms like .size, where we do have to do that, those are called O of n runtime algorithms, where n is the size of the list. Size, we have to go visit each node to figure out how many nodes there are in the list. String, toString, find, append, those are all O of n operators. So we got very efficient operations here. That's about all the time I'll have to talk about runtime because we got 6 minutes to do queue. Queue is similar to a stack, but different order. It's our first in, first out. So anytime you queue up for any line, that's the concept that we're talking about here. You queue up at the end and you're removed from the front. So our two methods here are InQ and DQ. InQ to the end of the queue and DQ from the front. So if we have this queue, we have an empty queue. We're going to InQ1 from the back. We're going to InQ2 from the back. We're going to InQ3 from the back. And then we're going to DQ from the front. So the first person who made it into that queue is the first one that's out of that queue. First in, first out. And here's our implementation. It's similar to a stack, but one huge difference here is that our link that we have to work with both ends of the queue. We're in-queuing from one end and de-queuing from the other end. So we can't get our efficiency quite as simply as we did with a stack. So the stack, we're only working on one end. We already have a reference to the head of the linked list. Everything's fairly straightforward with a stack in that sense, where we have to do extra work with a queue. So since we're working with both ends of the list, every time we want to in-queue, I'm going to in-queue at the end of the list. So we're going to append to the end of the list, and we're going to de-queue from the front. So we're going to remove from the front. So every time we want to in-queue a node, if we were just appending, we would have to do an O of n operation. Go dot next, dot next, dot next, dot next, dot next until we see null and then append. That's an O of n operation. Can't allow it. So what we'll do is one simple trick. We're going to store two references. Instead of just a reference to the first node in the linked list, we're also going to store a reference to the last node in the linked list. Now when we want to append, we don't have to traverse the whole list to find the end of the list, because we're going to keep track of it the entire time. We're going to always keep track of what the end of the list is. So when we have to append, we just say back.append. And we have to do a little bit more than that, as you'll see. So when we in-queue, we're going to go to the back of the list, and first we're going to check if back is null, because if the list is empty, then I guess I can do this part first. If the list is empty, we just create a new node. We're going to create a new node with a value, and next of null, we have a list of size 1, and assign that to back. And then since the list is size 1, the front and back are both the same, so we have to make sure front and back are both referring to that single node in the list. If the list is not empty, if the queue is not empty, then, well, we already have a reference to the last node in the list. We're going to create a new node and add that to the end of the list. So its new next is a new node that we're creating with the value that we're in queuing and a next of null, and update that reference to back to be that new node that we just created. When we want to dequeue, this is the same thing as popping from a stack. We're going to check if the front is null, just return null, that we're dequeuing from an empty queue. Otherwise, we're going to have a temporary value, storing the value of that node, which we're going to return. And we're going to update front to front's next. So we're going to remove that first node from the list. And then we have one extra check, only one extra thing we have to do for a queue, is if we dequeued the last node in this queue, we want to make sure we also update back, because back is referring to that last node right now. If we remove that node, we don't want back still referring to that node that was dequeued. We want to update back to also be null if the queue is empty. In our abbreviated memory diagram here, we have an empty queue. Front and back are both referring to null. We're going to in Q3, front and back are both referring to the new node that we just created. In Q7, this is going to update back to 7, but front is still a reference to that 3 because that's the first node in the list, the first value in this list. We're going to in Q2, update back to a reference to this new node we created. And a DQ, X is going to get that value 3, and front advances to this node. It's equal to the old front dot get next value. So we update the next, remove this node, it's garbage collected. DQ again, front goes to the next node, and X gets that value 7. DQ again, and here's where back is referring to this node of value 2. If we just do like we did with pop for a stack, front will refer to null, this node's next. But we want to make sure back is not still referring to this node after it's been removed from the queue, after it's been DQ'd. So when we DQ again, we want to make sure we also update back to null. If front is null, back has to also be assigned to null, and X gets this value 2. And if we DQ again, we actually are going to get a null pointer exception. Just the way that this is set up, it's kind of a strange situation. But we're going to return null. So we dequeue, we see front is null, so we return null. And then we try to store null into x, but x is a value of int. What null means is there's supposed to be a reference here and there isn't. But x is an int, a primitive value. Primitives aren't supposed to store references at all. So null being assigned to something that's not supposed to store reference at all doesn't work. That doesn't work, and then we actually do get an error. Can't assign null to a primitive. I think I said null pointer exception. It's not null pointer exception, but something to the effect of can't store null in a primitive. Can't do it. So we actually do crash. Just kind of a tidbit there. But that's how our queues work. And that's our last slide. And it's 10:30. Timing, baby. Can we dynamically allocate memory in C++? I have studies data structure in C, and here you are using STL. I'm not using C++ at all. You can dynamically allocate memory in C++ to answer the question. You can use malloc in C, and actually, is that true? I haven't touched C++ in a long time, but I believe you can, right? You can in C. I'm pretty sure you can in C++ as well. Not in Java. So this course is in Java, and we cannot dynamically allocate memory. We can't manage our own memory. The only way we can dynamically allocate memory is through constructor calls and through the keyword new. So this is going to allocate us memory, but once we're done with that queue, if we lose our references to this queue, it gets garbage collected instead of having to manage our own memory like we do in C and C++. All right, 10:30. Let's Right, that's it. Just a reminder, there are office hours. I have the 11 a.m. lecture. I have a half-hour break, then the 11 a.m. lecture for 2.5 hours, then another half-hour break, and then my office hours at 2 to 3. So if you have questions, I'll see you in office hours. If not, I'll see you on Thursday. Take care, everybody.